Okay, so we're going to continue our discussion from a week ago, or previous week, about spectral analysis and how to take a time domain signal, translate it to the frequency domain, and then gain some insights in terms of the signal that we're actually looking at, and then how we can maybe design circuits to condition it appropriately. Okay, so let's just go back to our idea of sampling a signal, okay, and just introduce a little bit of terminology. Okay, so here we have a continuous time signal, x of t, okay, and we want to sample it. Okay, we're going to look at it on our computer. So we're going to sample it like this. And again, the interval between these is given by our capital T, S. Okay? And we're just going to talk about some notation. Right? We have our continuous time signal, x of t. What we're going to define now is our sampled signal as x of n. Okay? And n here is just an integer, 1, 2, 3, 4, etc. Okay, and it just corresponds to the sample number, right? So this is sample number 1, sample number 2, 3, 4, and so forth. Okay, so we're just going to do this. This is how we're going to refer to a signal that's sampled in our computer as distinguished from the actual real-world signal outside. Okay, so what we want to do is take this signal, x of n, that we've sampled now, and translate it from this kind of time domain in terms of x of n, in terms of a sequence of samples, into a frequency domain, right? So we want to take this x of n, send it into something, and then get out something which describes that signal in terms of frequencies. So let's just call this another representation of x. We're just going to call it capital X, and talk about it in terms of frequencies. Okay? And so what's going to do this, like we've talked about before, this is Fourier. But in particular, when we're talking about sampled signals, the tool we're going to use is the fast Fourier transform. Okay, and this is a very efficient computation that you can implement very easily in computer software. And you'll see basically every software package that does something with signal processing will have some version of an FFT to it. Okay, and this is basically just saying it's doing our translation using Fourier from the time domain into the frequency domain, right? Okay, so you'll see people saying, okay, take an FFT of that. And it's just basically making this translation. Okay, and so you do FFT, and what you end up with then is it takes our signal x of n, and then it finds the sets of our amplitude coefficients and our phase coefficients. Again, these are the coefficients within our Fourier series, within our Fourier, that we're going to use in our Fourier equation to synthesize our signal, right? And then we can make our plots of our amplitude spectra, right? So AI versus frequency. So it'll look something like this. And then similarly with our phase spectra, right, which will have another kind of plot to it. Okay? So this is what we've talked about before, right? So just some basic questions here, right? So when we do FFT, first off, what's the number of samples, number of frequencies that are going to come out from FFT? Okay, and I'm not going to go through why this is in particular, but the number of frequencies that are returned by FFT are equal to the number of samples in our original signal. Okay, so if we have an x of n, let's say we have an x of n, which has 1,000 samples created by sampling something at 200 hertz, if this is our sampling rate. Okay, so 200 hertz, 200 samples per second, means we've sampled it for 5 seconds here. So then the number of frequencies that come out, in this case, we're going to get 1,000 frequencies for this particular case. Okay, so when we make our plot, we'll have 1,000 values of amplitudes and 1,000 values of phases. Okay, so another question to ask is that we've got this, amplitude versus frequency. So we could ask, what's the highest frequency here on my x-axis? So what's the highest frequency? That's returned by FFT. Okay, and this one, I don't think I have to assert, or you don't have to take me on faith, whereas this one you did, right? This one you can go back to what we talked about in terms of aliasing and sampling. Given a sampling rate, what's the highest frequency that we can see in a signal, right? It's the Nyquist frequency, right? So this is going to be equal to 1/2 of our sampling rate. Okay? So the x-axis, the highest frequency here, is going to be 1/2 of our sampling frequency. In our case, it's going to be equal to 100 hertz. Okay? So this is what's returned by FFT, right? And what we're going to do now going forward is talk about how we can look at these kinds of spectra. This is an amplitude spectra, but as you recall, we're often going to look at amplitude squared for our power spectrum. Okay? And we're really going to focus on this kind of a plot, this information here. This is telling us how much of different frequencies are present in our signal. And what we're going to do is just work through an example of this, how you might be able to use these kinds of plots to gain insights in terms of what is the nature of the signal that you're actually sampling. Okay? And then figure out, based on that information here, how to design maybe conditioning filters or try to debug aspects of how what the real world that you're actually measuring. Okay? So let's go walk through that.